In this video, we're going to start Chapter 5 of the statistics textbook. Chapter 5 is about the normal distribution, or the normal curve. Okay, so we just completed Chapter 4, which was on the average and the standard deviation. So far in Part 2, descriptive statistics, we've talked about the histogram and the average and the standard deviation. And just a reminder, everything we've talked about in Chapter 3 and Chapter 4 is focused on a single list of numbers. So a single list of numbers, what can you do with that? You can calculate the average, the standard deviation, the median, the range. You can make a histogram out of a single list of numbers. That can be confusing at first. You think histogram, you think X and Y axis. That's two different categories of data on the X and Y axis, right? That's what a graph is usually like. It's relating two or more variables, not with a histogram. A histogram is one list of numbers. The vertical axis is just a representation for the count. That's why with a histogram, you can calculate the average of a histogram, the range of a histogram, the standard deviation of a histogram. Okay, so we're still focusing on a single list of numbers. Yes, we've talked about studies that when data is collected in those studies, multiple different categories of data are collected for each subject in a study. But each of those categories is just its own list of numbers, right? Height, weight, age, whatever. So what are we talking about in Chapter 5, this normal distribution, normal curve? Well, remember in Chapter 4, so the main idea is you have the average of a list of numbers, and then the standard deviation represents how the values in that list are distributed around the average. If they're more spread out, the standard deviation is higher. If they're less spread out around the average, the standard deviation is lower. And what we talked about was that if you had a list of numbers and you didn't know how it was distributed around the average, so you might know the standard deviation, but you don't have the histogram, let's say. So you can't see exactly how it's distributed. Well, an assumption you could make that in a lot of cases would be a good assumption was we talked about you could say that 68% of the data points are within one standard deviation of the average, 95% are within two standard deviations, and pretty much all the data is within three standard deviations. Okay, so but where was that assumption coming from? That's what Chapter 5 is about. We're going to talk about where that assumption was coming from. What we were assuming was that the data was normally distributed around the average. That's what we were assuming. We were assuming that, again, we didn't know what the histogram of the list of numbers looked like. If we did, then we wouldn't need to make any assumption. We would just go by the histogram. We were assuming that the histogram curve looked something like this. And it was centered on the average. They show it here in this cartoon sketch. It looks something like this. That's what we were assuming. So here's the average. If you calculate the area under this curve within plus or minus one standard deviation, that's going to be 68%. If you calculate the area under the curve within plus or minus two standard deviations, that's 95%. If you calculate the area under the curve within plus or minus three standard deviations, that's like 99.5 or 9%. Okay, but before we get started with with Section 1, what I want to talk about is that, so in previous videos in Chapter 4, we saw lists of numbers that were nothing like that normal curve. For example, so there was a list of numbers like it was 49, 51. It was a series of 49s and 51s. So the histogram would be, it was like an equal number of 49s and 51s. Okay, well that's nothing like this. All of the data points are within one standard deviation. The standard deviation is 1. Every data point is within one standard deviation. And what you can imagine is you could come up with all kinds of lists of numbers that are nowhere near, if you make a histogram, they're nowhere near anything like the normal distribution is, anything like a curve like this. So where does this curve come from, and why do we use that curve as a general assumption for how a list of numbers is going to be distributed around the average? All right, well, think about what we went through in Section 1, which was on controlled experiments and observational studies. Okay, so yes, you can do statistics on any list of numbers. You can do statistics on anything you want. But the most common use of statistics is going to be on an experiment that was conducted. Or if it's not an experiment, then an observational study. So remember, observational study is you're sort of analyzing existing data, right? You go look, observational study, you look at, so the doctors collect data. They collect information about patients, about any patient before they, when they come in, their first visit. And so you look at that data and you try and analyze it. It's not an experiment. A controlled experiment, you're actually choosing the subjects, putting them into the groups you want, things like that. But right, that's the most common scenario that you're going to be doing statistics is when you're analyzing like observational study data, or you're analyzing experimental data from a controlled experiment. Okay. And so what we're about to talk about is that this normal curve here, this normal distribution for a histogram, what you can think of this as, it says here, you can think of it as an ideal histogram. It's an ideal histogram, and every histogram, no matter what it is some deviation from this ideal histogram. That's what the normal curve is. So why is it called the ideal histogram? Well, okay, so again, when you think about statistics, statistical data, a list of numbers, it can come from anywhere. A list of numbers can come from anywhere, but the most common scenario is observational study data, controlled experimental data. Well, okay, if we're going to think about even more than that, an ideal distribution, we would go to the controlled experiment, right? Observational studies can be useful, but ideally, no matter what it is, every single data set that you analyze would ideally be from a perfect controlled experiment. You do observational studies because it's quicker, it's cheaper, it's more practical in a lot of circumstances. But in a perfect world, all data that if you're trying to make a conclusion about something would come from like a perfect controlled experiment. And so what's a perfect controlled experiment? Everything is like perfectly randomized. We talk about randomized controlled. The data sets are sufficiently large. So the number of subjects is sufficiently large. Everything is random. All confounding variables have been accounted for. So in that case, if we're thinking about a list of numbers from that experiment, from a category in that experiment, you can imagine it's a sufficiently large amount of data. And also, let's just assume that it's not like just, a yes or no question with two possible answers. We're thinking about at least you have like a number of different possible values. There's no external variables at play. There's no bias at play. Everything is random. Then it's been found that the histogram of a list of numbers like that is going to closely follow this normal curve that we're about to talk about. And that's why all histograms or all statistical experimental observational study data is looked at from how much it matches or deviates from this normal curve. Okay, so the normal curve. The normal curve was discovered around 1720 by Abraham de Moivre while he was developing the mathematics of chance. His work will be discussed again in parts 4 and 5. Around 1870, the Belgian mathematician Adolphe Quetelet had the idea of using the curve as an ideal histogram to which histograms for data could be compared. Okay, so this normal curve, it wasn't invented when it was invented, it wasn't looked at as an ideal histogram, but it makes sense that, so what it started out as, it came from Abraham de Moivre. He developed it, he was studying the mathematics of chance, right? That's kind of what we would expect this normal curve to be based on, like chance, probabilities of getting certain values, the probability of something being within 1 standard deviation, 2 standard deviations. So I'm sure that was a big factor that Adolphe Quetelet considered, was that this comes from the mathematics of chance. And you think about these randomized controlled experiments, the data coming from those experiments, the way it's distributed would be based on chance. And he was right. So, again, if you take a sufficiently large set of random experimental data, it's sufficiently randomized, there's no bias, there's no external factors, it's random, it's going to follow this normal curve closely. That's what the histogram is going to look like. It's going to closely follow a normal curve. The normal curve has a formidable looking equation. Okay, so we know from algebra that with an equation of 2 variables, you can plot that in a plane. Well, if you want to plot the exact normal curve, in a Cartesian XY Cartesian plane, rectangular coordinate system, this is the formula right here. And why is it so complicated? Couldn't we come up with a simpler formula? Well, remember, we want it based on that mathematics of chance. We want to take straight from what de Moivre developed. In that case, it has the meaning that we're looking for. I mean, yeah, you could come up with any curve that's kind of close to this, and maybe it's simpler. But where would that curve come from? This is based on exactly what we would think randomized controlled experimental data would be based on, that chance, probabilities, because it's randomized. Okay, so you can work with this formula if you want. If you're good with calculus and you want to you can type this into your calculator as an integral. A graphing calculator can do a definite integral easily, so you could use this formula to find the area between any two x points on the curve. That's fine. But it's saying here, okay, we're going to find it easy to work with the normal curve through diagrams and tables without ever using the equation. Because that's what we're going to want to do is we're going to want to calculate areas within any interval we want, within any two x values. That's the main thing we're going to be doing with this normal curve. Okay, several features of this graph will be important. First, the graph is symmetric about 0. The part of the curve to the right of 0 is a mirror image of the part to the left. So yeah, notice this. If you were plotting this in an XY plane, it's going to be centered about 0, about the origin. Okay, and then what's the y-axis going to be? It's a density scale. It's percent per the units of the x-axis. So that's what this formula is. If you type in x is equal to 1, you're going to get this. Just under 25. And that represents, it's a density scale, percent per the horizontal unit. This percent per whatever this 1 means, whatever this 2 means, whatever this 3 means. So it's important to note that. This formula here, this normal curve, is based on this horizontal scale, which we haven't talked about what it means yet, but it's also based on the density scale. The density scale is percent per horizontal unit. So what does that mean? So if that's the case, then the total area under the curve equals 100%, right? That's what you would expect. The total area under this curve is equal to 100%. Areas come out in percent because the vertical axis uses the density scale. Okay, finally, the curve is always above the horizontal axis. It appears to stop between 3 and 4, but that's only because the curve gets so low there. Only about 600 thousandths of the area is outside the interval from -4 to 4, right? So what they're saying is, technically, this curve goes on to infinity and never touches the x-axis, the horizontal axis. Same thing here. It looks like it does, but it just gets so low that you can't see. You can't see in between the x-axis and the horizontal axis in the curve. But just note that outside of the interval from -4 to 4 is only about 6/100 thousandths of the area, of the total area. So if you're familiar with calculus, the idea is if you integrated this from x is equal to -infinity to infinity, you would get 100%. Anything that's not from -infinity to infinity is technically not 100%. But if you integrated from 4 to -4, you would get something very close to 100%, like 99.99%. That's the idea. It would be helpful to find areas under the normal curve between specified values. For instance, the area under the normal curve between -1 and +1 is 68%. Between -2 and +2 is 95%. Between -3 and +3 is 99.7%. So this should look familiar. This 68%, 95%. Why should this look familiar? Well, we talked about how the assumptions we were making in Chapter 4, when we didn't know the histogram, was that 68% of the data points were within 1 standard deviation, above or below the average. 95% were within 2. But what they're saying here, they're not talking about anything about standard deviation. They're just saying that between -1 and 1, the area is 68%, right? If you think about the density scale, it's actually the area would be, this is percent per horizontal unit. So if you take this area here, that's the length times the height, percent per horizontal unit times horizontal unit is just percent. So the area between -1 and 1 is 68%. -2 and 2 is 95%. So obviously these units here that they're calling standard units are related to the standard deviation. Okay. finding these areas is a matter of looking things up in a table or pushing a button on the right kind of calculator. The table will be explained in section 2. Okay, yeah, so you can find an area for any interval you want. I mean, if you know calculus and you know how to use your graphing calculator to do an integral, you could easily do a definite integral on your calculator with this formula. But again, we're going to see how we can use a table to do this, or there's actually built-in functions in your calculator to do it. You don't even have to do the integral, but we'll talk about this, the idea of the table in section 2. And I might do a video showing you how to use your calculator as well if you want. Many histograms for data are similar in shape to the normal curve, provided they are drawn to the same scale. Making the horizontal scales match up involves standard units. A value is converted to standard units by seeing how many standard deviations it is above or below the average. Okay, so what they're saying here is, we created a bunch of different histograms in chapter 3. And if we wanted to compare the shapes of those histograms to the normal curve, then you need to draw that histogram to the same scale as the normal curve, which means you need to convert the horizontal scale to standard units. Okay, and as it says here, and as we could have guessed, these standard units are how many standard deviations a value is away from the average. And in chapter 4, in the previous chapter, a lot of the example problems we worked, we did this. We were given values and we calculated how many standard deviations that value was away from the average. If it was within 1 standard deviation or within 2 standard deviations or 3. So we know how to do this. Now, the way they say this sentence here, many histograms for data are similar in shape to the normal curve, provided they are drawn to the same scale. It almost makes it sound like you're going to have a histogram that, just a typical histogram that we drew, that we made in chapter 3. And then you change the scale, and then the whole graph is just transformed into something you don't even recognize. That's not the case. It will change a little bit, and I'll explain why in a second. But you can imagine if you have your original histogram with the original units, you can mark off on that histogram where 1 standard deviation is, where 2 standard deviations are. And so when you think about that, the way that a graph could change, there's 2 ways that a graph could potentially change a good bit from when you shift to standard units. If the graph is really spread out, or conversely compressed in, then it might take the original curve and so the original curve might be more spread out, and it might pull it in a little bit, or stretch it out a little bit from here. And then also the shape might slightly change as well, because you're regrouping the data points into new bins. It's not that drastic of a change, but on your original units, you might have certain values in a bin that some of those values are within 1 standard deviation, and some other of those values are within 2 standard deviations, so they change bins. Okay, so let me show you what they mean here. If you make an original histogram, just like we did in chapter 3, and you want to convert it to standard units, how would you do that? Okay, here's the histogram we made in chapter 3. It was the batting averages of... So we pulled this data from sportsreference.com, and it's the league batting average each year from 2024 to 1880-something. We made a histogram out of these batting averages. Okay, that was this histogram here. Now, the way we made it, we used on the vertical axis. Originally, I just put percent, not percent per horizontal unit. I didn't do a density scale, and the reason is because for this case, the bin width, the batting average bin width was 0.0072. That's just the nature of batting averages. They're like these percentages, or like 0.2. The batting average the whole range was 0.237 to 0.309. So the bin width was 0.0072. And so if you take the percent, so like look here. Here's the percent. The percent of all the batting averages within the first bin was 7.1% of the count. 11 out of the 154. All right. If you take 7.1 divided by 0.0072, you get 992. And so the density scale is these really high numbers, and so I thought that was not very intuitive. So I decided to originally I just put the percent, but I put the density scale back just to show you how this, the going from the standard units, going from the original units to standard units with a density scale. And so this density scale is like, okay, if you want to know what's the percentage of data points in this bin here, you take 992.1 and you multiply it by the bin width, right? You get the area of the histogram, or you get the area of this block. 992.1 divided or times 0.0072 is 7.1%. So 7.1% of the data points are in this interval. That's the idea. Okay, and then when you convert this to standard units, you get this. So you can see, I mean, it does change shape a little bit, but it's not like it's this drastic change where you don't recognize the shape at all, right? It's close to the same thing, but it is different. It is a little bit different. Okay, so how did I convert this to standard units? All you're doing is, so here's our original list of numbers. Similar to how we calculated the standard deviation, we make a separate list of numbers next to the original list. Now, for the standard deviation, what we did was we first calculated the average of the batting averages. Then the separate list was the amount that data point differed from the average. So you had a separate list that was represented the deviations from the average. Then you took the RMS of that list of deviations, not the RMS of the original list, the RMS of the list of deviations, and that was the standard deviation. Okay, so to convert a histogram to standard units, similar to that, you create a separate list, and that separate list, though, it's not the deviation of that data point from the average, it's the number of standard deviations that data point deviates from the average. All right, and we calculated this a bunch of times in the previous chapter. What does that mean, the amount of standard deviations? Well, okay, you calculate the average of this list, you calculate the standard deviation, and then all you're doing is you say, okay, you do how much does this value deviate from the average, and that amount you divide by the standard deviation. So if the standard deviation is 3 units, and this value deviates from the average by 3 units, let's say above the average, then this is going to be 1. It's 1 standard deviation above the average, positive 1. If the standard deviation was or the standard deviation was 6, no, the standard deviation was 3, and this value was 6 units below the average, then this would be a -2. Okay, so with that, you get this separate list of numbers representing the standard deviations of each value from the average. With that list of numbers, you don't calculate the RMS, you just make a separate histogram with that list of numbers. That's it. So you do the same thing. You create separate bins, and typically just equal bin widths. Group all the data points will be in those bins, and you create a histogram. You go through the exact same process that we learned for creating a histogram, but with this separate list of numbers. That's it. That's exactly what this is. These on the horizontal axis, these represent standard deviations from the average. This group here, there was 7.6%, or no, this is a density scale. So 7.6 times the bin width was 0.6. 4.55% of the data points were less than 1.4 standard deviations from the average, but not less than 2 standard deviations. So within that range from the average. That's what all of these represent. Your horizontal axis is in standard units, and this is what you would compare to the normal curve. Okay, so we know how the horizontal axis, these two horizontal axes are related, but what about the vertical axes? And I did a density scale for each just because that's how the book does it, so I want to show you the density scale. But what it's going to be for standard units, okay, remember what this represents. This is percent per standard unit, right? This is percent per just whatever like the data points are, like percent per batting average unit, right? It's whatever you would call the units for these batting averages. So how are these related? How are these two vertical axes related? Well, this percent per standard unit, this is a percent per batting average kind of unit as well, except it's percent per one standard deviation of those batting averages. So what's one standard deviation? It's this here. It's the standard deviation of that list, this 0.013365. That's the standard deviation of the batting averages, right? So if you multiply, let's multiply 4,000 by 0.013365. $53.46. Now, these aren't aligned precisely, but this is just giving you an approximation. So in other words, if we actually lined up this axis and this axis to scale, the 4,000 would line up with 53.46. But you can see how that, you can just getting an approximate visual, that's about right. You know, these are about the same height. You see? Now, what about the percents? So you have this here. Okay, this is what we originally did with, you know, these numbers here are so huge. This 4,000. What was originally done was this is how we displayed the histogram in the original video. This is I would say is more presentable without those huge numbers, right? So this just represents this. The vertical scale is just telling you the percent of data points in that block, but it's not. You don't multiply the bin width times the height to get the percent. You just read off here. This tells you the percent within each block. Okay, this is a density scale. Let's convert this to, let's do the same thing here. Okay, now these aren't density scales anymore. These are just telling you the percent of data points within in that block. So how do these differ? You got 7.1 here, 4.5 here, 14.3 here, 16.88 here. This just has to do with the fact that what I mentioned a few minutes ago. You're just regrouping. Whenever you convert to standard units, one thing you're also doing is you're going to be regrouping some of the data points, because in this histogram here, you might have some data points within this block. Some are within one standard deviation, some are within two, or some are within 1.2 standard deviation, some are within 1.8. So they just regroup a little bit. That's it. Okay. And so here, what they do next is they reference from chapter 4 the Haynes 5 study, and it was the heights of women age 18 and over, and they give some examples of some data points, and you want to calculate that data point in standard units. So it's just like what I just talked about, but at the end of the video we'll do a couple examples to show this. But again, you already know how to do this. We did this in chapter 4. It's really simple. Okay, so it says standard units are used in figure 2. So yeah, here is the histogram for that heights of women in that Haynes 5 study. So in the background is the original histogram. Here's the units. And then they just put the standard unit axis here. And so I believe what they're doing here is they're not even rebinning. Like, they're not creating new bins in standard units and rebinning. You know, one way you could do it is you could just take your original bins, take the endpoints, convert those endpoints to standard units, and then just replace the horizontal axis with the standard unit axis. Just line it up where where one standard deviation below is, one standard deviation above is, you see? And so in that case, the histogram wouldn't even change shape. I think that's what they're doing here. I want to say that's what they're doing here, right? Because you can, for histograms, you can do any bins you want. You can choose the bin sizes you want. So if you want to, you could just use the original bins and just convert those endpoints to standard units, and you get the same thing. I mean, to me, it might be nice to have some clean endpoints in standard units, right? Like each bin size is a half of a standard unit, for example. If you do it this way, you're going to get some endpoints. Like here, they've got 63.5, 66.5, 69.5. If you just convert these endpoints to standard units, you're going to get some non-whole number or non-clean, not clean endpoints. But, well, okay, let's see. So the average was 63.5, standard deviation was 3. So there's the average. And then they do have it marked off, like this is 1 standard deviation. This is 2 standard deviations. So they've changed the axis even here, but you can see they haven't rebend though. Right? So because of that, those bend endpoints in standard units are going to be kind of random. So it's up to you. I mean, you can do it either way. You can do it like they have it shown here, or you can rebend in standard units. But again, like we talked about with the vertical axis, for the original histogram, it's just percent per inch, percent per the horizontal unit. But with the, at least as far with the density scale, but with the standard units, it's percent per standard unit. Well, what's a standard unit? In this case, the standard deviation is 3 inches, so it's percent per 3 inches. Well, okay, if we know every 1 inch is 20%, then the percent per 3 inches is going to be 60%, right? So here, if we knew that for the density scale, let's go back to the density scales. If the percent per a batting average unit was this 4,000, and then this is the percent per 1 standard deviation, well, how many batting average units are in a standard deviation? It's like 0.0135, 0.0133. So you multiply this by 0.0133, whatever it was, and you get something like this. 1 inch is 20%. There's 3 inches in a standard unit, so multiply this by 3. You get 60. Okay, the last chapter said that for many lists, roughly 60% of the entries are within 1 standard deviation of the average. So the average minus 1 standard deviation to the average plus a standard deviation. So within 1 standard deviation above or below the average, the normal curve says that 68% of the entries are going to be within that range. Right? That's where that figure comes from. You have the normal curve in the background. You can see that the original histogram, it was a good approximation. If we didn't know the shape of the original histogram, you can see that in the background. We used the normal curve approximation, and that was a good approximation, right? The original histogram follows that normal curve pretty good, and so I think what we got was, in reality, from the original histogram, this area within 1 standard deviation above or below was actually 71%. So you see the actual area. This is the crossed area here. That's the actual area of the actual histogram within 1 standard deviation. I believe that was 71%. The normal curve, if you calculate the area under the normal curve between 1 and minus 1, that's 68%. But that's a good approximation. Yeah, if we knew the shape of the histogram, well, we'll just use the actual area. Okay, and it was the same idea within 2 standard deviations. The normal curve, the area under the normal curve between plus 2 and minus 2 in standard units is 95%. And so we could do the same thing on the original curve in the background, calculate the area between minus 2 and 2, and I think it was 97% is what it actually was. The normal curve can be used to estimate the percentage of entries in an interval as follows. So yeah, if you don't have the exact histogram, or you don't have the histogram, so you need an estimate. First, convert the interval you're interested in to standard units. So you have the data points, but you don't have the histogram or something like that. You convert the interval that you're interested in to standard units. You want to find the percentage of entries in that interval. You want to estimate it. Convert that interval to standard units. Second, find the corresponding area under the normal curve in that interval, that standard unit interval. And then there you go. That's going to be your estimate for the percentage of data points in that interval. The method for getting areas will be explained in Section 2. Finally, Section 3 will put the 2 steps together. The whole procedure is called the normal approximation. The normal approximation. The approximation consists in replacing the original histogram by the normal curve before finding the area. Okay, so before we go to Section 2, let's do these problems real quick. Again, this is really easy. We did this a bunch of times in Chapter 4. All right, on a certain exam, the average of the scores was 50 and the standard deviation was 10. Convert each of the following scores to standard units. This is really easy. What is 60 in standard units here? 60 would be 1. It's 1 standard deviation above the average. It's 10 units above 50. The standard deviation is 10. What about 45? This is minus 1/2. It's 5 units below the average. 5 units is 1/2 of a standard deviation. What about 75? That's 25 units above the average. How many standard deviations is that? 25 divided by 10. 5/2. That's it. That's these 3 numbers in standard units. Find the scores which in standard units are. So now we're just going the opposite direction. If something has a standard unit of 0, what does that mean? That means it's equal to the average. If something has a standard unit of plus 1.5, what does that mean? That means it's 3/2, 1.5 standard deviations. So how many standard deviations? Like 3/2 standard deviations. That's 15 units. That means this value is 15 units above 50. This is 65. You see, 15 units. That's 3/2 of that's 1.5 of a standard deviation. So this is 65. What about minus 2.8? How many standard deviations is minus 2.8? Or no, minus 2.8 standard deviations. How many units is that? If something is 28 units above or below the average, that means it's 2.8 standard deviations above or below the average. This is 2.8 standard deviations below. What is 50 minus 28? 22. 22 is 28 units below the average. Convert each entry on the following list to standard units. That is, using the average and standard deviation of the list. Okay, let's do this in Excel. 13, 9, 11, 7, 10. Standard units. How do we convert these values to standard units? What's the average? What's the standard deviation? Okay, what formula do we use? Okay, we want to see, okay, the value minus the average. F4 here. Because we want to fix this cell reference, right? So this is telling you how many units above or below the average this value is, right? This is 3 units above the average. This is 1 unit below. This is equal to the average, right? But we want to know that we want that in standard deviations. How many standard deviations is this so above or below the average? So we divide it by the standard deviations. This is 1.5 standard deviations above. This is a half a standard deviation below, right? This is a half of a standard deviation below. Why is that? This is 9. This is 1 unit below, but a standard deviation is 2 units. That's a half of a standard deviation below. Okay, so we've converted this list to standard units. Now it wants us to find the average and standard deviation of the converted list. Okay. So let's do so the average is 0, the standard deviation is 1. Let's come here and let's find the average and standard deviation. So here's the original batting average list. Here is the standard units. Let's find the average and standard deviation of that. So I called this BASU. So equals to average zero and 1. Interesting. So I guess it looks like that's a property of, when you for any list, if you make a separate list that's in standard units, then the average of that list is going to be 0 and the standard deviation of that list is going to be 1. Cool.